Students, so in this video lecture we will be studying the designing of a 8-bit arithmetic and logic unit using VHDL. ALU is present inside every processor. So it is called the heart of a processor. Why? Because all the arithmetic and logical operations that can be performed using a particular processor, those operations are actually being done using this particular hardware called ALU, Arithmetic and Logic Unit. Now, what are the arithmetic operations? Their arithmetic operations are referred to the addition operation, subtraction operation, multiplication operation, division operation, increment, decrement. Those are called increment, decrement. These are called actually the arithmetic operations. Okay, and what do you mean by the logical operations? So logical operations means and, or, XOR, XNOR, NAND, NOR. Those are logical operations. Along with that, shifting, right shift, left shift, those are called logical operations. Okay, so arithmetic and logic unit can perform all these arithmetic and logical operations. So it's a hardware unit that can perform these different set of operations on the given two operands. So it has in the input two different operands on which it can perform different arithmetic and logical operations, and which operation will be performed, that depends on the select input of the ALU. Okay, that we'll see later in detail. But first of all, understand what is 8-bit. This 8-bit means, so you will when we discuss a ALU, we often call it 8-bit ALU or 16-bit ALU or 32-bit ALU. Similarly, in case of processor, we call it 32-bit processor or 64-bit processor. So what do you mean by this? So if we call it's a 8-bit ALU, that means the maximum size of the operands are of 8 bits. That means using this particular ALU, we can add a maximum 2 8-bit numbers at the same time. We can subtract 2 8-bit numbers. We can multiply. If the ALU is able to perform multiplication operation, then we can multiply at a time 2 8-bit numbers. Similarly, it's also applicable for the logical operations. So we can at a time add 2 and 2 8-bit numbers, or 2 8-bit numbers, XOR 2 8-bit numbers. Okay, we can apply the shifting operations on a 8-bit number. Okay, so that is why we call it 8-bit ALU. If it can perform this on 16-bit operands, then we will call it a 16-bit ALU. If it is a 32-bit operand, then 32-bit ALU. 64-bit, then 64-bit ALU. Okay, so in this particular lecture, we will be studying the designing of a 8-bit ALU. So it has two 8-bit operands on which it will perform different arithmetic and logical operations. Now, next thing we must know that what are the other different units of a processor. So a processor, if we draw a rough diagram of a processor P, so it has ALU, already we have discussed. It has also registers, different registers, and also a control circuit. So roughly these are the three important units of a processor, and processor is connected using bus. So the parts, address bus, data bus, control signals, all are there inside this particular bus. Bus are nothing but interconnecting wires, set of interconnecting wires. Okay, so using this bus, the processor is connected to the memory unit, and also with the input output unit. So in a typical example of a processor, input can be a keyboard, output can be a display. Okay, so and you need to know that processor cannot exist without memory. So there will be always a memory. In fact, all the instructions we generally write on this memory. Okay, and then we send the initial address or starting address of the instructions to the processor, and once we send this to the processor will start execution of those instructions one by one using the help of this bus. Okay, so in this case it will be using the address bus and data bus. In the address bus it will send the corresponding address of the memory block. Using the data bus it will fetch the data. Okay, and ultimately if we write some instruction related to addition, the addition operation will be done inside this ALU. Okay, and before the addition is done, the data fetched from the memory will be temporarily stored in the register. In fact, after the addition, the result will be also stored in the register, unless we write some instruction in the memory to store that particular data from this internal register of the microprocessor to some memory cell present in the same memory. Okay, so this is the basic block diagram of a computer. Okay, and we will be designing this particular ALU. Let us this particular ALU block of a processor in this particular. This is the block diagram of a simple 8-bit ALU which we will be designing in this particular lecture. In general, the block diagram of ALU is represented like this using this particular symbol. So let us understand the different input and output pins of this ALU. So as we have told already, it has two inputs, input A, input B, and as it is a 8-bit ALU, so input A, input B both are of 8 bits. If we mention the size using the language VHDL, then it will be 7 down to 0 for both A and B. And similarly, the output is also of 8 bits, so this is the output of the ALU. The size is 7 down to 0. So this particular ALU will perform different arithmetic and logical operations. So in this case, we are targeting two arithmetic operations, add, subtract, and two logical operations, and let us use different color, then it will be okay. Two logical operations and or using this particular ALU. So given these two inputs, input A and input B, any of the four operations can be performed depending on the signal select. So if the size of this select signal is 1 down to 0, it's of 2 bits, as you can see. So why 2 bits? Because this ALU can perform 4 different operations. So to select one of these 4 different operations, we need at least 2 bits, right? So in this case, we will get 4 different unique combinations of 2 digits, 2 bits, 0001, 1011. So each of this bit sequence, 2-bit sequence, tells this ALU to perform one of this operation, add, sub, and or. And there are few output signals also you need to understand. So CO is the carry out signal. If it is addition operation, then CO is the carry out bit. Okay. If it is a subtraction operation, you know that V indicates the overflow. So actually these two signals, CO and V, this comes at the output of the adder subtractor unit that we have discussed in our last class. Okay. So obviously the addition and subtraction operation will be performed inside this 8-bit ALU using that particular adder subtractor unit. So we'll be calling this particular adder subtractor unit as a component inside this ALU. Okay. And as that adder subtractor unit has these two particular outputs, so this particular outputs will also be available at the output of ALU. 0 and S is the sign bit. So these are two signals that will be set or reset depending on the output. So depending on the output means depending on the output of ALU. So if the output of ALU is all 0, it's a 8-bit 0, so 8 zeros, then in that case the 0 will be 1, this output Z will be 1, and the sign, obviously the sign bit, this is the output, sign output represents the MSB of the output out ALU. So if the MSB of the out ALU is 1, then sign will be 1. If it is 0, then sign will be 0. So each of these outputs CO, V, Z and S are 1-bit signals, output signals, and they show the status of the result out ALU. Okay. This is the functional description table of the ALU which we'll be designing. It contains the information that depending on which combination of the select signal, which operation will be performed. So as you can see, if the select signal is 0 0, then addition and operation will be performed. If 0 1, then OR. If 1 0, then addition. If 1 1, then subtraction operation will be performed. How we have obtained this particular information that this select signals will be performing this particular operation? To understand that, we need to understand the internal diagram of the ALU. So let us explore the internal diagram of the ALU. In this particular slide, we can see the internal diagram of our targeted ALU and its different blocks present inside this and how they are interconnected. Okay, so let us first identify that what are the different sub-modules present in this ALU module. So as you can see, this is the AND 8-bit module. This is responsible for performing the ANDing operation. So it is AND 8-bit, means it has 8 AND gates which are required in order to perform this A and B operation. As we know, both A and B, these two operands are of 8 bits. So actually, to get the output, we need bitwise AND operation. That means A0 will be ANDed with B0, A1 will be ANDed with B1, in the same way A7 will be ANDed with B7 in order to obtain the output. Similarly, this OR 8-bit, this particular sub-module is responsible for performing the OR operation, and as you can understand, it needs how many? 8 OR gates in order to implement this OR operation, A or B. Okay. As we have discussed, to perform the addition and subtraction operation, we are using this add sub unit. Okay, add sub 8-bit that we have already designed in our last lecture. We will be just calling it. Okay, the other modules we need to design it. Okay, now let us understand the different input and outputs of this add sub unit. So we already know that these are the two inputs, A and B, each of them are of 8 bits, and this is the output, sum output, this is of 8 bits, and this is the overflow output, V, and this is the carry out output, CO, and this is the input, M. This depending on this signal, addition or subtraction operation will be performed, any one of them. So if M is 1, then you know subtraction will be performed. If M is 0, then addition will be performed. As you can see in this particular internal diagram of the ALU, this M input signal is connected to the select 1. So the MSB of the select signal is directly connected to this M input. So you can understand, if select 1 is 1, then subtraction will be performed. If it is 0, then addition will be performed. Let us understand the other units also. So we have used two Muxes multiplexers. So they are 2:1 multiplexers, as it has 2 input lines and 1 output line, but each of these input lines are of 8 bits. So we will name them Mux 2 to 1 8-bit. So we'll name this module as mux221 8-bit. Why? Because inputs are of 8 bits. So if you can remember the operation of multiplexer, then it has a select input. Depending on the select input, one of the output will be connected to the one of the input will be connected to the output. If select input is 0, then this upper input will be connected to the output, else if select is 1, then this lower one will be connected to the output. Okay. Similarly, this is also 2:1 mux. So let us understand which operation will be performed, or which of the output of these 3 blocks will be connected to the result depending on the values of select signal. So let us start with 0 0 select signal. So when select signal is 0 0, as you can see, this upper port will be connected to the output, and it is also 0, the upper one will be connected to the output. So as you can see, the AND operation will be performed because the output of AND gate is connected to the result. So as you can see, output of the AND gate will be available at result, so AND operation will be performed here. Now let us understand the effect of other combinations of the select signal. Let us understand the combination 1 0. So when select 1 is 1, what will happen? This lower input of mux1 will be connected to the output, and at is 0, then upper port will be connected to the output. So as you can see, the output of OR unit or module will be connected to the result. So OR operation will be performed when select 1 is 1, select 0 is 0. Okay. Next combination of the select signal is, let us understand, 0 1. So when select 1 is 0, what will happen? This upper port will be connected to the output of this mux, but this output will not go to the output result. Why? Because this input of the mux is 1, so that means this output of the add subunit will be directly connected to the result in this case. Then what is the effect of this select 1 on the result? It has an effect. Why? Because as you can see, this select 1 is going to the input of the add subunit as M input. It's connected to the M input. So as M input is 0, that means addition will be performed. So when select 1 is 0, select 0 is 1, addition operation will be performed. Okay. So let us understand the other left out operation condition of select signal is 1 1. So when 1 1 is the select signal, as you can see, the output of add subunit will be connected to the result, and this one is going to the input M of the add subunit. That is why subtraction operation will be performed. So subtraction operation will be performed when both select 1 and select 0 is 1 1. Okay. You should note that in this functional description table we have written the select 0 first, then select 1. Okay. That means for this particular combination, select 0 is 0, select 1 is 1. Okay. Let us understand the sub-modules which are used to obtain the status signals. So as you can see, overflow and carry, these two status signals are directly obtained from the output of add subunit. Okay. So it's simple, very simple. Just you need to directly connect this output ports to the output port of add subunit and our job will be done. But how to get this 0 and negative signal? Negative is nothing but the sign output that we have already discussed in the block diagram of ALU. So sign output will directly come as the MSB of the result. Okay, it's also very simple. Now how to obtain this 0? To obtain this 0, we have used this 8 input OR gate, and at the output of this OR gate, one NOT gate is connected. That means actually we are performing 8-bit NOR operation. So we need 8-bit NOR gate, 8-bit NOR gate in order to implement this 0 signal. As you can see, if all these bits of the result are 0, output of this OR gate will be 0. That means output of the NOT gate will be 1. so 0 will be 1. Otherwise, if any bits of this result is 1, then output of this OR gate will be 1 and output of this NOT gate will be 0. That means result 0 flag will be 0. But if all the bits of the result output is 0, in that case the output will be 1. Essentially we are performing the NOR operation. We are having a NOR gate which has how many? 8 inputs, 8 inputs. So 8 inputs, 8 bit NOR gate. So for this, the sub module which we will be using in our VHDL project, we will name this particular sub module as NOR 8-bit. Okay. So as we have already discussed the different sub modules which we require in order to implement this 8-bit ALU module, so let us make the list of this sub module first. It will be easier for you to prepare the sub modules then. So how many? First one is this AND 8-bit module. Second one is this OR 8-bit module. Third sub module which we need is the ADD sub module. Fourth one which we need is the MUX. So this 8 input MUXes. Fifth one we need this NOR gate. Okay. So accordingly we will design this 5 sub modules and we will be calling these modules inside our top module 8-bit ALU as components, and inside this top level module what we will be doing, we will be interconnecting them in order to design this 8-bit ALU using VHDL. For this purpose we need to first identify what are the input and output ports. We know the input ports are A, B of 8 bits. Select 1, select 0. Select is an input port also, it's of 2 bits. And the output ports are, the main output port is this result which is of 8 bits. Other output ports are the status outputs. 0, negative is denoted with this sign bit. Overflow, and overflow is denoted with V, and the carry out, CO. Okay, so these are the 4 output output ports having a single bit width, so scalar ports. Okay, so let us go to the ISE project navigator, create a new project. Let us give the name ALU 8-bit ALU 8-bit. Now click on next, finish. Already the project has been created. Now right click on this, add, click on new source, VHDL module. First let us create the top level module, so let us give the same name, ALU 8-bit. Next, create, mention the port names. So port are A, input port, obviously bus, how many bit width is 8, so 7 down to 0. Similarly B is also input port of bus, 7 with 7 down to 0 with another is select input. So select input is direction is input, and 1 down to 0, so this is the width. Now let us define the outputs. So output we can define as result. So result is the output, RES. It's obviously 7 down to 0, and we need to mention the direction as out. Another is let us start with the carry out. So CO is the carry out, we know it's output. Overflow, V is the overflow, it's also out. 0, Z is the 0, it's also output port, and the sign bit is also the output. So all the port declarations has been done. So click on next, click on finish. So already it has created the corresponding entity description of ALU 8-bit. Okay, now let us identify now what are the different submodules we need in order to implement this ALU. So already we know that the submodules we require are this AND 8-bit or 8-bit. So let us design first this AND 8-bit. Okay. Let us leave this top level module incomplete over here, and let us start designing one by one the sub modules. Okay, so we'll start with AND 8-bit. Okay, so the procedure is same. Click on this, right click on this, create new source, VHDL module, give a name and okay, so click on next. So AND 8-bit, if you look at the module, corresponding module, it has two input ports A and B. Each of these input ports are of 8-bit width, and output port, single output port. You can name this output port as Y of bit width 8. Okay, so simple design. A input bus 7 down to 0. Next is B input bus 7 down to 0. Output Y. This is out. It's also bus 7 down to 0. Next. Okay. Now let us design this particular module using data flow style. Okay. So because it's very simple. Style. So it will be very ridiculous if you try to design each and every gates and then you use structure later in order to design this AND 8-bit. So this design is very simple. You do not need to break it into simple designs because itself the design is simple. So you just mention design this using data flow. Do not go to the structure way of design. So Y, we know that. So let us start with Y0, or we can directly write this Y equals to A and single line where we consider each of these variables Y, A and B signals actually are vectors. We could have written OR statements for each individual bits from 0 to 7. So in that case Y0 will be assigned as A0 and B0. Y1 is assigned as A1 and B1. This way Y7 is assigned as A7 and B7. But we do not require to write down all those 8 statements because this one single statement is sufficient. Why? Because here each of these signals are of same bit width 8. So we can use, instead of this 8 different statements, a single statement using vector signals. Okay. So let us try to simulate this design for synthesize this design first. To do this, we need to assign this AND 8-bit module as the top module. To do that, right click on this, set as top module. Yes. So it's not the top module of our design, but to synthesize this module, we need to select this, make it as the top module. Otherwise, we cannot synthesize it. Now, double click on this. It will synthesize the module. If some error or warning is there, it will show. So you need to remember that after synthesis, we need to simulate each of these submodules. But to shorten the time duration of this lecture, we are skipping this. Okay, but you must simulate all these submodules in order to check their functionality, where it's functionally correct or not. Okay, so already it has synthesized with no errors and warning messages. Okay, so we can click on the technology schematic to see the corresponding. So this is the diagram of AND 8-bit. Obviously AB are input, Y is the output. Each of them are of 7 bits. So if you look into that, it is using LUTs in order to implement that AND gate. And how many LUTs it requires? It requires 8 LUTs. 1, 2, 3, 4, 5, 6, 7, 8. So 8 AND gates two input AND gates it requires. So they are implemented using LUTs, 8 LUTs. If you click any one of them, so schematic of this LUT, the functionality this LUT lookup table is implementing is of a two input AND gate. As you can see, the equation is very simple, AND gate equation, and this is the truth table. Okay, so likewise all the LUTs will have the same kind of truth table and implementation structure. So it has already implemented. Let us design the next submodule, odd 8 bit. Okay, odd gate. So to do that, create another new source VHDL file. So we'll be creating another VHDL file, VHDL module, name as odd 8 bit. Next, obviously it will have the same kind of input. A, it's a bus 7 down to 0. B, another input, it's also bus size 7 down to 0, 7 down to 0, and output Y, it's output signal, it's also a bus 7 down to 0. Next, finish. So it will already create the entity description of the odd 8 bit module. Now we'll be using the same kind of statements, data first style of designing in order to implement the architecture. So we name this data flow. Also need to rename the end name of the architecture, that is data flow. Now Y equals to A or B. So this will implement the 8-bit OR gate, and how we have already discussed, because each of these signals A, B and Y are of same size is 8 bits, so it will easily implement the bitwise OR operation between A and B and store the result in one. So let us save the design, click on this OR. Now we need to make it as a top level module, otherwise we cannot synthesize this. It has top level module, yes. So let's synthesize this, double click on that and synthesize this. Now this module also we need to simulate after synthesis. Why? Because otherwise if some error exists in our design, then in future when we will be calling this sub modules one by one in the main module, top level module, then if there's some error occurs, it will be very difficult to understand or to find out from which submodule this error is occurring, or this error is not from any submodule, it's from interconnection. But if we functionally verify all these individual submodules before using them in the top level module, then what will happen, we'll be very sure that no error is there in our submodule. They are functionally correct. So the error must be in the main module, in the top level module. There must be error in interconnecting the submodules. Okay. So right now it has synthesized successfully without any error and warning. You can do one thing, you can go to the technology schematic to view this. So same kind of diagram, it is also using the same 8 LUTs in order to implement this. So if I double click on any of one of this LUT, it will show you the implementation of a OR gate. So yes, as you can see, it's implementing 2 input OR gate. This is the equation and this is the truth table. Likewise, if you select any one of this LUT, you will get the same kind of implementation. Okay. In this top level module, our ALU, the AND gate and the OR gate we have already designed. This AND module and OR module has been designed. Now next thing we need to design is the add sub 8-bit module. So we have already designed this add sub 8-bit module in our last lecture, and I have copied all the VHDL files. So it requires, as if you can remember, it requires a full adder file. So I have copied this full adder file and the main module, the add sub 8-bit module, which calls this 8 full adder modules in order to implement the add submodule, and also it requires several um, data flow style of statements in order to implement the overflow bit out and the XOR operations, XOR gates, which are required in order to make it a control adder subtractor unit. Okay, so in our main program, we will copy paste one by one all these modules. So Control A, Control C. Now here we will be creating. Let us copy the top module first. So our top module was this one, add sub 8 bits. So let us copy this module first. Same procedure, new source, VHDL module. Now with same name, add sub. If you can remember the naming convention, it was add sub 8 bit. So capital B, and these D's are small d. We need to provide the same name, 8 capital B. Otherwise, what you can do, you can add this VHDL file in our directory, but I'm not adding it. Instead, I'm creating a new file. Okay. So for the time being, let us just leave this, finish. We have already created add sub 8 bits. So Control A, delete everything, paste the module. So add sub 8 bit is done. Save it. So see, once you save it, it will automatically demand for this full adder modules. So now right click on this, new source, VHDL module, name as FA, next. Just keep this procedure, save, finish. Now here we need to copy the full adder description. So this one, Control A, C. So I'm copying everything. Now Control A, delete everything, paste our full adder module over here. Done. Now you can do one thing. You can click on this add sub module, make it a top level module, set as top level module, and now synthesize this. So hopefully it will be also synthesized successfully without any error and warning messages. You can see the adder subtractor module has been synthesized successfully without any error and warning messages, as we have already discussed. It will be. Now the next module which we need to design is the mux. So it is a 2 to 1 mux. Each of these input ports are of 8 bits. So let us design a new VHDL file under the same project directory, VHDL module. So give it a name, mux 2 to 1 8 bit. Next. So how many inputs will be there? Inputs are I0, I0. This is the input bus. Obviously, each of these inputs will be of 8 bits. Next input is I1. So it's also a bus, size 7 down to 0. And it needs a select signal. Okay. So I'm just naming it as S. S has how many? S is also bus, or it's a scalar signal. S is a scalar signal because it's a 2:1 mux. So the size of the select signal will be of a single bit. When it is 0, I0 will be selected. When it is 1, I1 will be selected. Okay, so it's simple in. It's a scalar signal. Output Y. It's output, and it's a vector signal with the same size 7 down to 0 as with the input signals. Click on next, finish. As you can see, so we will be now designing the mux. So we can design the mux entirely using data flow style of design. So you can write like this. data flow, data flow. Let us write down the expression which we need in order to implement this mux. So y is assigned as, if you can remember, it is actually I0 input 0 S bar input 0 and S bar, or input 1 and S. So it is a simple statement. A is, if we consider A and B are two inputs, then A S bar plus BS. When AS is 0, y will be equals to A. When S is 1, y will be equals to B. So this is the simple statement of a one input mux, but here we need to remember that each of the inputs are of 8 bits. So first of all, without considering the size of the inputs, that inputs are vector and output is also vector, let us try to implement this 2:1 mux. Okay, so y is equal to y0 and not of s. Obviously, let us put it inside a bracket, or I1 and S. So this is the simple statement. But if we now try to simulate this design, it will show you error. Why? Because the size of each of these signals, I0, S, I1, they are not same. Though Y, I0 and I1, each of them are vector signals of size 8 bits, but S is a scalar signal, so we cannot write this kind of statement. So the modification, instead of using this single statement, now we need to use 8 different statements for 0th bit, for 1th bit, for 2nd bit, in this way for 7th bit. Okay. So how to do that? So simply write y0 is equals to I00 S. Now I000 is a single bit, so we can easily AND it with the S bar. I10 obviously, and it with this. So now it can synthesize this. So we need how many? 8 such statements. So let's copy this, paste it 8 times. 4, 5, 6, 7, 8. Done. Now rename this 1, 2, 3, 4, 5, 6, 7. And this is also 7, 5, 4, 3, 2, 1. This is also 1, 2, 3, 4, 5, 6, and 7. Done. Save it. Now we need to synthesize this design. How to synthesize this design? Now to do that, we need to right click on this module and make it a top module. So set it as top module. Next, double click on synthesize. ESC has successfully synthesized this mux, and it doesn't show any error or warning messages. So now we need to view the schematic. So view technology schematic, start with the module. So as you can see, these are the inputs. S is the select signal and this is the output Y. Double click on this, so you'll get this kind of module. So as you can see, this is same kind of structure. So it is implementing this module using lookup tables. So it needs 8 LUTs in order to implement that. Each of these LUTs are implementing each of the statements we have written in data flow style, each of the expressions. So this is for bit 0, this is for 1, this is for 2, in this way this is for 8. Okay, so one thing you need to carefully observe, that the 0th bit of I0 is connected to I2 of the input 2 of a lookup table, and I10 is connected to the I1, and I0 input of this lookup table is actually connected to the select signal. Okay, so I0 is actually connected to the select signal. So with this information, let us click on this lookup table. As you can see, it is implementing a mux 2:1 mux. Okay, as you can see, this is the basic circuit of a 2:1 mux. We can also verify the truth table. It's also the truth table of a 2:1 mux. Considering that I0 is the select signal. I0 is the select signal. I1 and I2 are the inputs. Okay. The last module which we need to design in order to complete this ALU design. So we need to complete this design of this last module, a NOR gate. So it's a 8 input NOR gate. Let us try to implement this design. So same procedure. First of all, close all these windows. Okay. Looks clumsy. Click on this, right click on this, new source, VHDL module. Okay. Now we are implementing NOR get NOR 8 input. 8 input. Next. So let us define the input signal as I. So this is the input. Obviously it will be a size 7 down to 0. How many inputs are there? This 8 inputs. So we are considering, instead of 8 scalar signals, one vector signal I of size 7 down to 0, and output is Y, and it is the output signal, direction is output, and output in this case is of single bit. If you look at this, output is of single bit, goes to the 0. Okay. Next, finish. It has already created this module, NOR input. Now let us use the data flow style of design in order to implement this also. Data flow, data flow. Now y equals to not of, this is the last not which we are implementing, not of or of I0 to I7. So let us write down all this. I0 or I1 or this, let us copy this. Okay, this will be I2, 3, 4, 5, 6, 7. So now let us select this particular module, NOR 8 input, as the top module and synthesize this. Hopefully it will be also synthesized without any error. Let's see. Now I request all of you to simulate this particular module also. Okay, and also the previous marks module. Yes, it has synthesized it successfully without any error or warning messages. Let's see the technology schematic. So this is the technology schematic. As you can see, it has been implemented like this. So these two lookup tables are used in order to implement this. Hopefully, if you look at the structure or table of this lookup table, then it implements the NOR operations only. You can see also RTL structure of the module. So now, as you can see in the RTL structure, as it's a very simple gate, so the RTL schematic comes without any error or bug. So from the RTL schematic, you can easily verify this, whether it's a lookup, it's a NOR gate or not. Yes, it's a NOR gate, 8 input NOR gate, as you can simply verify this. But if you want to verify this from the technology schematic, then you need to really go through the lookup table design. So both these lookup tables you need to go through in order to see that. Okay. After this designing of NOR 8 input module, we need to functionally verify it by simulating. Okay. So to reduce the size of this video, again we are not simulating this module. Rather, will be now going through the top module in order to interconnect all these all sub modules inside the top module and interconnect them in order to incomplete ALU 8-bit module, and we need to now complete this module. So before we do so, we need to select this particular module ALU 8-bit as our top level module. Set as top level module. Now let us rename this. We will be using structural style of design. Structural. So the name of the architecture will be structural in our case. Now one by one write down all the component declaration statements. So start with AND get. So this AND get. So double click on this and it will show you the corresponding VHDL file, and copy this entity declaration statement. So it will be easier for you to, and go back to this top level module, paste this one. Replace entity with component, and component statements doesn't require this is. Component statements ends with in component. Done. Next is this add sub module. Okay. So now copy the entities declaration statement of add sub module, paste it over here. So rename accordingly. Component add sub, no is required. Component. Done. Now next is, if you scroll down, we do not need to call this full adder statement, because full adder statements we are not directly calling. It has been already called inside the add sub module. We do not require to declare the component, use it as a component again inside our top level module. So next is marks. Okay. So marks, copy this module, go back to the ALU marks. So replace this entity with component. Component doesn't require any is. Paste it here. Next is the NOR gate. So go to that file, copy the entity statement, come back to the original one, replace this as component. We do not require any is keyword, ends within component. Done. The next one is the last one, odd 8-bit. Okay. So odd 8-bit one, copy, paste over here. Component doesn't require any is. Paste. So all the component declaration statements we have written in the top level module A. Okay. Now we need to write down the signal statements. Okay. So obviously we'll be using several signals because there are interconnecting wires. So let us find out the interconnecting wires first. Signals to be used. Let us go to the diagram. So this is the diagram of the ALU. Let us find out the interconnecting wires which are not connected to directly the input output ports. Okay. So if you see, look at this wires, they are directly connected to the input port A and B. So they are not internal wires. Okay. So similarly, this overflow and carry, these are connected to directly the output ports. These are not internal wires. So which are internal wires? This is an internal wire, not connected directly to any input or output port. This is an internal wire. This is an internal wire. This is also an internal wire. Also, if you see, it looks like this is an internal wire, but this is not an internal wire. This is actually connected to the result output. So result, actually the result port we need to use as an in-out port. Okay, because the result signal is also used as an input to this 8-input NOR gate in order to determine the 0 output signal 0. Okay. So let us name it accordingly. So for this particular wire, name it as internal signal 1, this name as internal signal 2, this internal signal 3, and this is as internal signal 4. Okay, and you need to remember that each of these internal signals are of 8-bit width. So they will be vector signals of size 8. So we need to declare 8 such signals. Okay, first signal int1, okay, and it will be a vector signal. S type std underscore logic underscore vector, size is same as 0, 7 down to 0. So we need to declare 3 more such signals. Okay. Int 2, 3, and 4. Done. Now we'll be using these signals in order to interconnect all these components. We must write all the constitution statement of the AND gate. So if you look at the corresponding ALU internal circuit diagram, so input of the AND gate is connected directly to the A and B inputs of the ALU, and output is connected to the int1 internal signal. Okay, so let us give a suitable label. So and 8. Okay. Now copy this name. The module name is and 8-bit. As you can see, A and B are the inputs, then Y. This is the sequence in which we need to write. So put map A and B obviously is connected to the A and B input of the our top level entity A and B, and Y should be connected to this internal one, this signal. So int 1. Done. Next, let us write down the component instantiation statement of the OR gate. So this will be OR 8, label is OR 8, and obviously the name is OR 8-bit, OR 8-bit, and it has also the same sequence, first A and B, then Y. Here also the A and B inputs are connected to the A and B inputs of the ALU, and Y, the output is connected to the int2 signal. As you can see, the output of this OR gate is connected to the int2 signal. Okay, done. Next, let us write down the add sum module. So add sum, this will be a suitable label to this, and let us copy the name of the module, and also let us remember the sequence A, B, then M, then S, then CO, then B. Okay, port map. Again, in this case, A and B are connected to the A and B of the ALU. Then M. So M was connected to the, if you look at the corresponding diagram, then M is connected to the select input 1. So M is connected to the select input 1. Okay. So let us write down the statement select 1. Then the next signal was S, then CO, then B. S is connected to the internal signal int 4. So let us write down that S is connected to int 4. CO is connected obviously to the CO output signal, CO, this one, and V is connected to the output B. CO, and then V is connected to the output B. Now next, let us write down the component instantiation statements for the marks is. So we'll start with this particular marks, then we'll write down this marks. Okay. So let us identify the inputs. The inputs of this marks is int1, int2, and output is connected to int3, and the select line is connected to select 1. Here input is connected to int3, then int4, and then select line is connected to select 0. Output is connected to the result signal. Okay. So keeping these things in mind, let us write down the corresponding. Start with marks 1. So let us give the name marks 1. Okay, then copy the corresponding component name, mux 2218 bit, port map. Okay, and remember that these are I0, I1 first, then S, then Y. Inputs are given first, then the select line, then the Y. Then we know that inputs are connected to I0 is connected to int 1, I1 is connected to int 2, and select line is connected to select 1, and the output is connected to int 3 for the first mux. Okay, for the second mux, let us name the mux 2. The first internal signal, let us again go to the diagram. So this I0 is connected to int 3, I1 is connected to int 4, int 3, int 4, select is connected to select 0. Okay, so let us write down int 3, then int 4, and it is select 0, and output is connected to the result of this result. Okay, now next we need to write down the component instantiation of the or NOR gate NOR8. So let us keep the name NOR8. Okay, copy this NOR8 name of the NOR8 module. It has the port map. It has NOR8 gate has input port I, which is the 8-bit input, and Y is the output port. So input then output. Let us identify how they are connected. So input is connected to the result signal. Okay, and result we are using as input to this. So we need to change the direction of this result signal in the entity description of ALU as in out. Okay, I is connected to result, and output Y is connected to Z. Okay, result, and Y is connected to set, and along with that we need to modify the direction of result as in out, otherwise it will show you some error or warning messages. Okay, after synthesis. Now all the modules we have already called inside the top level module, except we did not connect this negative, this sign bit. The sign bit should be directly connected to the 7th bit of the result signal. So result 7 should be directly connected to the sign bit. Let us write down the corresponding statement using data flow style. So basically we are using a structural style of design, because now along with this component instantiation statements we are going to use another expression. So S, write down the expression as S equals to result 7. Okay, and along with that we need to change. Okay, so result 7 is also already connected, result is already mentioned as an in out port, and also if you go through the component instantiation statement of this add sum module, as you can see the CO is connected to the CO of the ALU. Okay, carry out of the ALU. But if you look at the corresponding add sum module, then in that add sum module CO is mentioned as in out, because CO we required the CO signal again inside some expression which we needed to implement this adder subtractor module. So CO was again read by the module itself. So that is why it is declared as an in out port. So as this CO is connected to the CO of our main module, so this CO also we need to mention as in out. Okay, otherwise it will show you some error or warning message during synthesis. Now let us select this top level module and synthesize it. Okay, the ISE simulator already synthesized our ALU module successfully without any error or warning messages. Okay, so let us view the corresponding schematics. Start with RTL schematic. So this is the RTL schematic of our ALU. This is the top level module. Inputs are A and B, and select input, and outputs are this. Result is the main output, and other status outputs CO, Z, B, and S. Okay. So if you double click on that, you will get the internal diagram. So as you can see, these are the modules which we have used: and 8-bit, odd 8-bit. We have used two to one marks, one ADSum module and one NOD module, and also you can see that the S output is directly connected to 7 pin. Okay, so this is the complete diagram. As you can see, as we have uh, tried to implement or to interconnect all these modules, we have successfully connected in the same way all this module. If you check the interconnections, you will find the same interconnections are there in all these cases. Okay, and you can also double click on each of this module and you can see the internal diagram. It's an AND gate, 8 input AND gate. This is the OR gate. This is marks, as you can see. This will be the ADSum module. This is the NOR module. This is another marks. Okay. Now if you double click on the technology schematic, you'll get the corresponding implementation target for the FPGA platform. So if you double click on that, the entire ALU has been implemented using the lookup tables. Okay. So here it will be very difficult to find out all the individual modules, but if you see the names, corresponding names, you'll be finding them. So as you can see, this is the ADSum module. Okay. So if you double click on the corresponding LUTs, you will get the corresponding implementation structure or the content of these LUTs. Okay. Now, as we have already synthesized this successfully, let us try to simulate this module. To simulate that, just close this first. Go to the simulation window and then click on this ALU. Hit new source. VHDL test bench. Obviously, name it a test. Next, select the module which we want to test. Obviously, ALU 8-bit. This is the module which we want to test. Next, and finish. It will create the VHDL test bench. So as you can see, this same kind of test bench has been created. So clock, we need to delete this clock process because right now in this particular module we do not have any clock signal. Remove this, and here we need to write down we need to assign some signals to the inputs. And what are the different inputs? In this particular module we have A, B and select inputs. So we'll give different values to this A, B and select inputs. Okay. So let us start with some random value of A. A equals to any value, let us give. Suppose 001, 0011, 1. Okay. So it must be of 8 bits. B 0 1 0 1 1 0 0 0. Okay. Then select. So first let us use the corresponding bit patterns of select signal which implements AND operation. Okay. So to identify that, let us go to the PPT. So this is the corresponding table, and we need to remember that the select 0 bit is written first, then select 1. So for AND operation, both are them 0 0. So we need to select accordingly 0 0. Then it will perform AND operation first. Okay. Then we'll write down some wait statement to do that, and copy this, paste over here, paste it 4 times. So here, after waiting for 100 nanoseconds again, with the same A and B, let us perform the OR operation. To perform OR operation, we need to change the select signal as 0 1. So 0 1 means 0 is the LSB, 1 is the MSB. So 1 0 in the test bench, we need to write down 1 0. Okay. Then after waiting for 100 nanoseconds with the same A and B, let us perform the addition operation. For addition operation, we need to make it 1 0 means 0 1. So here we need to mention 0 1. And lastly, for subtraction operation, 1 1 should be the select input. So with the same A and B, we are performing different operation at different time instant through the different select signals. Okay. Let us save this, but particular test bench file, click on this. First, check the syntax. Okay, it's correct. Then simulate the behavior and model. Okay, now zoom to the full view. Here you can see different inputs: A, B, select input, and the corresponding simulated outputs, result output, then CO, then B, then Z, then S. So as you can see, before 100 nanosecond, every input A, B, and select was 0, 0, 0. So that is why the output was also 0, all 0. And thus the 0 output, the 0 status signal was 1. Why? Because all the output bits are 0. Okay. As you can see, at the next time, at 100 nanosecond time instant, the select signal change, the A and B signals changes. Okay, but the select signal remains 0, 0. And 0, 0 select signal means we need to perform the ALU should perform the AND operation. So, is it performing the AND operation? Let us check. To check that, we need to check the bits of result. So as you can see, 0, 0 and it's 0, 0 and 1, then 0, 0, 1 and 0, then 0, 0 and 1, 0. So 0 and 1, 0, again 1 and 0, 0, 1 and 0, 0, 1 and 0, 0. So all 0. And again it is all 0, that is why the 0 status signal remains at 1, logic level 1. So it is successfully performing the AND operation when the select signal is 0, 0. At 200 nanosecond, again the select signal changes 1, 0, it becomes 1, 0. So now it should perform the OR operation. So let us check it whether it is performing the OR operation or not. So OR operation means 0 or 0, so 0, 0 or 1, so 1, 1 or 0, 1, 0, 1, 1, and 0 or 1, 1, 0 or 1, 1, 1 or 0, 1, 1 or 0, 1, 1 or 0, 1. Okay, so the result is correctly ORing the inputs A and B. Okay, 0 and 1, 1. And as you can see, no longer the result is all 0, that is why the 0 flag has come down to 0 again. Okay, and also if you look at the sign bit is 0, so that is why S is also 0, and CO and B has not been used. Actually they are used, but they are not reflecting we will not be using their values. CO and B has been generated because already these are added in the add sum modules, and accordingly CO and B has been generated, but we will not be using them or checking them. Why? Because in the AND operation we do not need CO and B. In the OR operation also we do not need CO and B. So that is why we are not checking the corresponding status. But we need to always check the status Z and S, because they will be all for all the operations they are valid. CO and B, these two status signals are only valid for the uh, arithmetic operations. They are not valid for the corresponding logical operations. Okay, and all. So and that is why we are not checking. Again, at 300 nanosecond, the select signal becomes 0 and 0, 1. So that is why we need to subtract this to check whether it is to add this 0, 1, select signal 0, 1 means we need to add the ALU should add the A and B inputs. Okay, whether it is currently adding the A and B inputs, to check that we need to change the radix from uh, binary to sign decimal. Okay, again for B, binary to sign decimal. For the result also we need to change the radix sign decimal. Now, as you can see, at this time instant, A is 39, B is 88, and the result is addition of this. If you add 39 plus 88 becomes 127, so result is 127. It's correctly adding 38 and 88, the inputs. Okay. And during the addition, no CO carry out or B is generated, so CO and B both are 0, 0. And also, if you look at the corresponding binary representation of the result, you'll find that the sign bit is 0, the most significant bit of the result is 0, and also the 0 flag is 0 because the result is not 0, all 0. If the result was all 0, then in that case it would be 0, but right now it is 127, so obviously result is non-zero. That is why the 0 flag is reset to 0. Okay. Let us check the next operation at sorry, at 300 nanosecond. Uh, at 300 at 400 nanosecond, the select input becomes 1 1. So select input becomes 1 1. That means now the ALU should perform the subtraction operation with the same A and B, because throughout this operations we are not changing A and B. A is 39, B is 88, so it's performing 39 minus 88, and the result is minus 49, which is the correct one. Okay, and as you can see, the result is negative, and if you look at the corresponding binary representation, you will find that the MSB is 1. So that is why the sign bit is also 1, showing that the result is negative. And zero flag is 0, because the result is negative, it is non-zero, that is why the zero flag is 0. And if you look at the V and CO, they are also 0. Okay, so it's correctly our ALU is correctly implementing all these 4 operations with the corresponding select signals. Okay, we have functionally verified our ALU. Also at the 500 nanosecond, as we have not given any wait statement at the end of our process, so the process repeats itself, and again the select signal becomes 0 0 at the 500 nanosecond, and AND operation has been performed with the given input, and it repeats itself, then OR operation, then again sub addition operation, then again subtraction. Okay, you have understood the designing procedure of ALU. This is a simple ALU. You need to remember that the actual structure of ALU will be much complex than this, and the select inputs will not be like 2 bit in size. They will be much more than that, so that the ALU can perform much more operations. Okay, and also, you need to remember that the design of ALU we have performed using structural way. In that case, each and every submodules we have designed on our own. So, you could have designed this particular ALU using behavioral way also. In that case, you can use a case statement in order to determine in order to represent the functionality of ALU. Okay, it will be very simple. Okay, if you go through if you search it in Google, you will find out the corresponding case statement representation, case statement syntax for VHDL, and also probably you will find out the corresponding code of 8-bit ALU with that. So case in the as a case variable, you should consider the select. It's very intuitive, and if select is 0 0, then you should perform the AND operation. If it is 0 1, then corresponding operations. So in this way, for all the combination of select input, you need to perform the corresponding operation. Okay, you just mention it in the behavioral way of designing, behavioral description inside a case statement. But in that case, what will happen? The internal structure, the hardware, actual hardware of the corresponding ALU will be may not be optimized, because it will be completely generated or synthesized by this simulator itself. So we are not specifying the hardware on our own. So it completely depends on the uh, efficiency of the software, that how much optimized hardware we will be obtaining at the end. Okay, so that is why we are not designing our ALU using behavioral way, but as we have mentioned, while designing any circuit, hardware circuit, we design it in both ways, in structural way, then in the behavioral way also, because it will be helpful to verify the output of this, or verify the functionality of the of our design. Okay, and it's the convention to design the hardware in both the ways. Okay, but we need to remember that if we are designing it in a structural way, then we can design each and every module on our own, and our final design, the top level module, will be more optimized as we wished it to be. Okay, so if we want to design some low power module inside this, we can do that corresponding modification in the hardware. Okay, so it completely depends on us how we are designing. and obviously it's more time consuming in structural way, and it's very less time consuming in case of behavioral way. So this design choices depends on the complexity of the circuit and also the application.